The shortest statement of Fermat's sums of two squares theorem, part 2, which states that every prime of modularity 4n plus 1 can be written as the sum of two integers squared. So what is the story behind the quadratic f of x equals 10x squared minus 14x plus 5? In August 2019, I uploaded the video Negative Pythagorean Quartets, two more infinite series, and we are only interested in the one that I labelled the fourth infinite series. So I took the fourth series and restated it as the Fibonacci identity, the answers for which were all multiples of 5 times a 4n plus 1 prime, or composite, and which are shown in the bold blue font. When fed into a regression program, it spat out the quadratic equation of interest f of x equals 10x squared minus 14x plus 5. The linear equations for the roots of the sums of two squares were revised as shown by the blue bold font, so that a n equaled the x input for the quadratic equation. Attaching the output from the quadratic to a primality checking program, we can sort the primes from the composites and then give the sum of two squares solution for the prime at the same time by the following algorithm. Remembering that n equals x, so for x equals 3, and referencing back to the original Fibonacci identities in our example, we have d equals 7 times 3 minus 5 equals 16. C equals 5 times 3 minus 3 equals 12. B equals 5 times 3 minus 4 equals 11. A equals 1 times 3 equals 3, which gives 16 squared plus 3 squared equals 12 squared plus 11 squared equals 265 equals 5 times 53. Working the simpleton method for the sum of two squares backwards, we find by pairing the two even and two odd results that 16 plus 12 divided by 2 equals 14, 16 minus 12 all divided by 2 equals 2, 11 plus 3 all divided by 2 equals 7, 11 minus 3 all divided by 2 equals 4. Hence we have 14, 2, 7 and 4, which we pair as 7 and 2 and 14 and 4, where we see that one is the double of the other. And we find this for all results, which reflects the fact that the factor 5 is equal to 2 squared plus 1 squared. Hence we find that 7 squared plus 2 squared is equal to 16 squared plus 3 squared divided by 5 is equal to 12 squared plus 11 squared divided by 5 equals 53. Applying what we have just done to the first 10 Fibonacci identities, we obtain the following tabulated results. So for n equals x, the input into the polynomial, we see that the resulting sum of two squares is given by f of x is equal to 3x minus 2 all squared plus x minus 1 all squared, an infinite sequence that gives either a 4n plus 1 prime or a 4n plus 1 composite. Since the output can be either prime or composite, we can only get one sum of two squares by this method, as dictated by the prime output, whilst a composite result dictates that at least two sum of two square solutions exist. We can conclude that 1. We have started from an infinite sequence of Fibonacci identities, which means that every pair of sums of two squares are the product of at least two 4n plus 1 primes, one of which is 5. 2. Likewise, the sequence of sums of two squares we have deduced from the initial Fibonacci identities give rise to only 4n plus 1 primes or composites, as they are all contained in the initial Fibonacci identities. 3. We note that both the sequences on the preceding slide contain all the integers from 1 to infinity as one of the roots of any pair of sums of squares. Thus, 16 squared plus 5 squared and 30 squared plus 5 squared are both members of the infinite sequence 5 squared plus 2n squared for n equals 0 to infinity, and likewise for all other pairs. So what we have is, as per part 1, for a equals 0 to infinity, the simpleton's quadratic theorem, f of x equals 2x squared minus 8x plus k, where constant k is equal to 2n minus 1 squared plus 4 for n equals 1 to infinity, since every quadratic f of x then outputs every odd 4n plus 1 number, prime and composite, as per above table, that is the sum of two squares, QEF. From what has been shown, it is to say the least 1. Impossible, 2. An absurdity, and 3. Just plain stupidity to conjecture that a prime of modularity 4n plus 1 could exist that was not a sum of two squares. This slide shows 3 100-digit primes and the roots of their sums of two squares obtained by feeding the results from the quadratic f of x equals 10x squared minus 14x plus 5 into my primality checking program. The program tested 176 results to obtain the 3 primes, and the program completed in just under a minute and a half. Not bad, eh? The simpleton's mathematical coat of arms. In Euclid we trust, and not mathematicians. That's all, folks. Till next time.